Start now. Thanks. The second session this morning. So the first talk will be presented by Alexander Milovanov, who is in NEA, Frascati. Yours is you also. It's going to be about staircases and Schrödinger, nonlinear Schrödinger.
Yeah, right? It will be mostly about nonlinear Schrödinger equation. So indeed, I will start with the staircase, but you know, the keyword, however, will be another C, nonlinear Schrödinger. So, first of all, thank you, Guglielmo, and thank you, the organizers, for inviting me. I'm really very pleased to be here at Aix-en-Provence, and like many of you, it's my first in-person conference since the pandemic, I think. So, I acknowledge my colleagues and co-authors, Jens Juel Rasmussen from Technical University of Denmark, with whom we collaborate since more than 20 years. And we had quite some works on anomalous transport and fusion plasma. And with Guglielmo, we started exciting works a little bit more recently, and especially our collaboration has referred to plasma staircase and nonlinear avalanche transport associated with the staircase. However, in my talk of today, actually, I do not intend to be too much fusion oriented, even though maybe I'm supposed to be, given that I'm mostly paid for being involved with the fusion, but I allow myself to be a little bit more relaxed, and I will speak mostly about things related with nonlinear dynamics. That's what interests me and what I suppose is my field. So I gradually start. Concerning the staircase, you know, I will assume that most of you are familiar with this phenomenon. So it is really not up to me to tell you what is it. Many of you are the inventors of this phenomenon, and you know it better than me. So it's me to learn from you then rather than for you to learn from me. So I will be only very sketchy on this. Just maybe thinking that it could be that there is someone occasionally not quite familiar with what a staircase is. So just I limit myself to very brief literature sketch, which is not comprehensive literature in many ways. Just to mention that the phenomenon was predicted first, theoretically, it was developed by Guglielmo with co-workers. It was a physical review paper, rapid communication from 2010. Then it was discovered experimentally, actually, Abu de Saploums on Torsopra tokamak. It was a fantastic paper, physical review letters. That was actually about the year when we started to collaborate with Guglielmo. And in 2016, we were lucky to write and to win an enabling research project, and that were 2 fantastic years during which we were quite working on this business, and there were a handful of publications coming up. So here maybe are only few papers that could be among the most important, but it's not a full list of papers. At the same time, it appears that the phenomenon has spread, and there were other groups working on this similar business. You might know these publications as well. And well, important thing for a physicist is that the phenomenon has been observed not only on Torsopra, but now also on other tokamaks, among which is D3D, the K-star, the accelerators. So it seems that there is a robust phenomenon which we may seriously be talking about. In a nutshell, the phenomenon just tells you one very simple thing, that it appears that zonal flows in a tokamak have structure. That is, by some mechanism, colloidal flows tend to be self-organized into very narrow and very intense jets, like this. These bands, dark bands, going from down up. At the same time, the spacing between the jets appears to be interspersed with some transport phenomena, which looks like non-local events. and they are characterized as avalanches propagating in radial direction. So here the avalanches are just these small fine structures a bit going with inclination along the normalized small tokamak radius. So here are the transport events, and here are the toroidal flows. So this picture, it comes from numerical simulations with the Gisela code. And again, I acknowledge Guglielmo, who it was his courtesy to give me this picture for presentation. It gives you, just in a nutshell, a feeling what is it. It looks like that the staircase occurs in both regimes, like separated atomic confinement and linear atomic confinement, and mostly I think it refers to L mode plasma, not H mode. So that's almost all about the fusion flavor of the phenomena. But the promise is that I told we shall meet nonlinear Schrödinger equation, and that's what I'm going now to tell. The idea is actually very simple. Somehow this idea is, it was born here in Provence. It dates back to 2019. I was on a visit at Cadarache. We were discussing with Guglielmo. Also, I think Jens was visiting occasionally for other conference, fusion conference, and it was born. We just felt that the phenomenon could be described in terms of nonlinear Schrödinger equation. With which motivation? Just let us look in a boloidal cross-section, how the boloidal flows are organized. So the jet flows, if you look in a boloidal cross-section, that would go roughly in a periodic fashion, as they should. So this is an oscillator. There is a period, rotation period, and characteristic frequency, characteristic wavelength, just the length of the contour. There are many such oscillators. Apparently, they not independent, since we assume that there is an avalanche transport, then these oscillators can exchange mass, they can exchange momentum, they can exchange energy, and the mechanism somehow refers to involves Rayleigh stress. So there is a feeling that such oscillators would be coupled. So this system is actually a system of nonlinear coupled oscillators. Then why not to describe this system, the whole staircase system, as a system of coupled nonlinear oscillators, or a wave packet of oscillators? Then, which would be a good way or most natural way to characterize a system of coupled nonlinear oscillators or a wave packet? I would say nonlinear Schrödinger equation. Schrödinger equation, linear, it comes from the inspiration of Schrödinger. It simply says that if we have time, which is translation invariant, then translation invariance of time conserves the energy. And Schrödinger put it in an operator form. So this is about the linear part. Then the nonlinear part, which is nonlinear frequency shift, it refers to our university courses of mathematical analysis. That is, when you expand a function close to in vicinity of a point, then a first nonlinear correction would go with a quadratic amendment. So you will get something like a quadratic term into this equation. So it would go like this, on inspiration of Schrödinger, with something that refers to Taylor expansion. But if you just put here a quadratic term, just anticipating something, it will simply not work as well as we wished. So at some point we felt that you need to put here not a quadratic power, but a subquadratic power. This is also an inspiration in many ways. An inspiration which has some background. The background refers to another fact from the analysis, that Taylor expansion with quadratic term is actually not the most general form of expanding a function. Well, we get used to it because we are taught at the university course that quadratic correction is the most natural and the only way to expand the function. But in reality, it assumes that the function must be rather smooth and based certain properties. And those properties are not the most general properties. In effect, we can introduce a class of functions that maybe not as smooth as those functions that we used to study at mathematical courses at the university, but they are enough smooth when you integrate them. So you convolve such functions with the power law, with a kernel, and you obtain a new function which is smooth enough. And such functions are called now in mathematics integral differential functions. So this is a more general class of functions which comprises those functions to which we are used to from standard courses. And then for that class of generalized functions, their Taylor expansion would start with the algebraic term, not with quadratic term. So with this motivation, we put here a power s, and we assume that s is between 0 and 1. So here we have a subquadratic power. And this is one part of the story. Another part of the story that, of course, this inspiration.
Before you go on with the story, could you comment at all on how you would actually come to this kind of structures systematically from kind of one of the standard plasma models? In other words, in less polite terms, where do you get equation 1 from without pulling it out of thin air?
So this is the question which pulls me to the domain which I wish to avoid, because when I told that I wish not to be involved with the fusion and I wish to give a talk from the perspective of nonlinear dynamics, I wish to bypass this problem, but you pull me back. To some extent, this refers to what Yannick was presenting in the morning. It refers to the general physics of zonal flows, but I guess there is something else to it, since we relatively well understand how the zonal flows are. But there is something to it which says that the zonal flows are not really homogeneous, but they tend to produce a structure. And there is a current debate how it really works. So we can write plasma fusion equations, but I mean, there are many. First, we wish to understand which basic physics ingredient we wish to put in it and how it works on a macroscopic level. And this can be debatable.
I mean, can you indicate some reductive perturbation theory or any one of the other goodies that actually produces this structure?
I'm not sure. I understand your question.
Particularly with the S away from 1.
You know, I'm a bit skeptical of using perturbation theory in this context, since to me, it's not perturbative. You know, it's a non-local and strongly coupled system. So how to describe it by perturbing something? I would say that not. We can, by perturbing, obtain something like Gaussian or diffusive behavior, but we have to deal with transport which goes on avalanches. So to me, it still remains at the level of, I don't wish to use self-organized criticality, since a rather strong term and it's not quite applicable in this context, maybe.
But even in self-organized criticality, you can construct hydrodynamic models, for example, in the style of Waugh and Tardai. I mean, there, you know, on the basis, say, of basic trends and symmetry arguments.
I can partly agree, but partly, you know, since I mean, so far we were not able to describe self-organized criticality starting from fluid equations, and I'm even doubtful that they would produce you the nice properties of avalanche behavior. So it's all becoming kinetic, in my opinion. You can put it on a lattice and just run particles and allow them to jump somehow, but it's kinetic. It's not hydrodynamic. To me, there are many plasma processes here at play. So one thing that we can produce superdiffusive transport in a radial direction, but other thing that how to couple the various particles propagating superdiffusively in radial direction and how to produce from individual particles a coherent structures, which would be avalanches. This is a great business. Non-perturbative business in many ways. There were other questions.
More like also comments to what Pat asked about motivation of this equation. I mean, maybe it is obvious for some of the people here, but there's a correspondence between Milovanov and Schrödinger equation. It's of course different system that you described here, but it's a known phenomenon that if you take the limit h bar going to 0 of the Vlasov-Kosovo equation, then you of the Schrödinger equation, then you get the Vlasov-Kosovo equation. So although your equation are a bit different in nature, I would say, but if you, for example, take S equal to unity, then it looks at least the two first term on the right hand side look for me like equivalent system for like a Schrödinger equation that I'm aware of how it behaves in the moment.
No, you know, Vlasov-Kosovo equation is a different story in many ways. It comes from the Liouville theorem, right? Why you need to twist it in? I wish to remain within a equation which contains the necessary ingredients to me. That is the energy conservation plus nonlinearity. And I might not know, although I know, but I might not know anything about Vlasov-Maxwell system here, you know. By the way, you are perfectly right, and that's what would be my point to where sooner or later I might be arriving if I have time today, that I can derive kinetic equations similar to Vlasov-Kosovo equation, actually in a little bit more correct form, just starting from the nonlinear Schrödinger equation. That would be my conclusion. So if I speak, I probably arrive to it.
Okay.
Yeah. But I don't wish to put anything else from the outset, you know. I wish to have two input ideas. One is the idea of Schrödinger, that if time is translation invariant, then energy is conserved. In cosmology, you know, it can be all debitable. I'm not really sure that energy is conserved in cosmology. Okay. But well, for those times which we used to work on Earth, well, maybe it is to some extent is correct. And then we have some nonlinear correction to it. So we put some quadratic term. Now, it all appear maybe a little bit mysterious in this fashion that, well, I just put algebraic nonlinearity, and now I'm going to do something about it. In reality, you know, there was some background, of course, in my case. So it's not just came so occasionally and unexpectedly. Somehow, for many years, I was involved in the studies of phenomenon, you know, Anderson localization, that is localization of waves by random scatterings in disordered media. You know the Anderson phenomena, the claim that if you put a wave and it is reflected by random inhomogeneities, then it is somehow localized and there is no transport of waves there. Then there was a great business suggesting that Anderson localization may be destroyed if you add a nonlinear term to it. So if you put a quadratic nonlinearity, then under some conditions it appears that Anderson localization is destroyed. And I got involved with it with my colleagues from the Technion in Israel. It was now 12 years as doing this business. And of course, we used various models like this Schrödinger model with random potential analysis and various types of nonlinearity. And we tried the different approaches. So we studied first quadratic nonlinearity in a classical setting, then we studied superquadratic nonlinearity in a classical setting, then subquadratic in a classical setting, turned to quantum equations, and we used also quantum forms of nonlinear Schrödinger equation with quadratic, subquadratic, and superquadratic nonlinearities. So we somehow knew how it works. And based on all that knowledge, which here I completely omit, were a dozen of papers which came out of this, I just felt that a staircase can be in many ways similar to the Anderson problem. So if you add a subquadratic nonlinearity, it will produce you the properties that you expect otherwise in fusion equation from basic fusion stuff. And somehow it works, at least statistically it works that way. So this it was an inspiration in some sense, but inspiration with the background. That's what I want to say in a nutshell. Just one element here. I'm sorry, I will be a little bit more maybe into mathematics today, but I don't expect you to follow all details of the derivation, even though I will show you something maybe looking a little bit complex, but just follow me in the sense of main idea and main approach. I don't mean that you go through all details. So one problem, of course, if we go ahead with this analogy to Anderson problem, is to speculate if there is a basis for our wave function psi. So if we assume that staircase can be described by a sort of wave function that we would love to expand it over a basis of eigenmodes. But does this basis exist? For Anderson problem, yes, it exists, but there is also a great business to explain why. So I believe that a similar argument can be advocated for staircase physics, but the motivation has something to do with the fact that in toroidal geometry, basically your colloidal flows tend to be concentrated, maybe close or attracted by positions where your safety factor has rational value, and rationals, they are everywhere dense in the real numbers. So that's the nutshell of the argument, that there is a basis by which you can expand the wave function. So I assume that you can expand it. And then there is a great mathematical theorem which says that when you strongly need something, you can do. So suppose now I just wish to tell you a little bit how to deal with this type of equation when nonlinearity is subquadratic. But first, maybe if it is quadratic, so you know how to expand your wave function over a basis. Then no problem, you know how to write this modulus psi squared. So this gives you a double sum with a complex conjugate. So in this equation, you just multiply both sides by complex conjugate and sum over wave number and use orthogonal condition. And at the end of the day, out of this, you get an equation of motion, which is just the standard equation for coupled nonlinear oscillators. Just this is the oscillatory part linear, and this is the coupling part. So this equation simply tells you that, well, we have a system of infinite number of oscillators, so all of them are coupled according to this scheme, like it's on the right side. But this is quadratic, so and rather straightforward. But if it is subquadratic, then it's a little bit more trickier. So of course, one thing you can argue that what is power 2s of a psi function. I would say the most natural way to understand this would be to say that this is power s of square. Then if you expand, you have double sum again, like in quadratic case, but now you need to raise it to power s. And this is going to be non-trivial. So we had to learn somehow how to do it. Now, here, well, the solution was partly we found it with Sasha Yonen when we were looking into this equation in quantum case, and partly we learned it with Jens and with Guglielm when we already started to apply it to staircase physics. And the idea, at least mathematical technical idea, is like this. If s is integer, just forget about that this is fractional and smaller than 1. If s were integer, then in principle, you can write this expansion. And for this, you have a multinomial theorem. So it will tell you that this expansion would be exactly a sum with multinomial coefficients of some products raised to powers. And these powers are such that they are solution to this equation here. So the sum of these powers must be each time equal to s, where s is integer. But that, and for multinomial coefficients, we have also the standard expansion. But this is integer. So we said at some point, okay, but let's try to write the same thing, just forgetting that s is non-integer, but try to understand if it can be somehow applied for fractional values. Then with the factorial function, it's easy. It goes as gamma function, so you can calculate the coefficients. Okay, but with these guys, it's a bit less trivial. And then we propose that then one can deal with it in a sort of perturbative fashion. I mean, perturbative, it's not in conflict with what I was saying before in response to what Diamond was asking me for perturbative approach. It's just perturbative way to deal with this sum with fractional s. The idea is that we can develop a perturbation expansion of this sum for fractional s, but in a bit tricky way. In the first order, we just consider a situation according to which there is only one fractional exponent in this expansion and others are integer. In the second order, we allow 2 fractional exponents and other integers. In the next order, we have 3 fractional exponents and all other integers, and so on up to infinity. And it seems that this form of perturbation theory, which is not really perturbation theory, but some form of dealing with fractional power by iterative procedure, it works. So it generates a series expansion which seems to converge and converge rather fast. And I give you an argument why it converges. But let us see first, if there is only 1 fractional exponent, then it's very simple to see. If one of the exponent is equal to S, then the sum of others, which are integer exponents, then the sum of integer exponents is 0. And those integer exponents are non-negative, obviously, because if they are somehow negative, then you have a trouble with wave function being small. You will get a divergence, so they cannot be negative. And then you have that the sum of integer non-negative exponents is 0, and then all these exponents are 0. Then this equation is reduced essentially to 1 term when you have only 1 fractional exponent, and you get this simplified form for expanded wave function. And you see it involves 2 wave processes coupled with some parameter S. And then you go to second iteration, and then you have you have 2 fractional exponents, and their sum must be S, and S is smaller than 1. And then the sum of all other exponents that are non-integer, that are integer non-negative exponents is 0. So all those exponents must be 0 then. And you have these 2, and this corresponds actually to 2 terms in your product. So you have 1 to power 1 fractional power and the other fractional power, and it needs 4 waves now. And you will see that so on and so forth. The more fractional exponents you allow in this expansion, the more waves you need to couple. But the more waves you need to couple, the lower the cross section will be. So it will be actually a factor which exponentially decays with the number of waves that are coupled. So in many ways, you can even reduce and forget about the rest of the expansion and go only in the first leading term, which occurs when you have only 1 fractional exponent. So with Sasha Yomin, we call that backbone mapping, backbone approximation. And we leave the high order terms apart. Of course, it's a business now to understand when we can really forget about the high order terms and when we might not forget about them. It's not so trivial. And my present way of thinking that there are situations when you might not be so easily forgetting about them. So in some situations, you need to reinstall all terms, but probably it's not for staircase. So for staircase, our conclusion was that's enough going backbone approximation. So if we do that, reducing ourselves to backbone and doing the same kind of stuff with the fractional S value, we actually obtain again an equation of motion for coupled nonlinear oscillators, which is linear term, and these are nonlinear coupling term. And that contrast with the quadratic case, you have some fractional powers here. And that works. It gives a simple way. Now, second step here is to see the structure of this nonlinear term. So how it really couples all these nonlinear amplitudes. Fortunately, there is a very fine structure here, in the sense that you may naturally map it on a Kelly tree, in a sense that each amplitude may be represented by incoming or outgoing node, and each linear oscillator by just a node on a Kelly tree. So you will, out of this system of nonlinear oscillators, you can just produce a Kelly tree represented in terms of a Kelly tree, in which each node is an oscillator and the coupling terms are just outgoing or ingoing branches, outgoing ordinary wave amplitudes and ingoing complex conjugate amplitudes. Then you need to also assign some meaning to this parameter S, which appears that it would be a kind of fractal dimension of the node. So when S is 1, then you have a full node, but if S is smaller than 1, it goes like a counter set of it. And you explore the properties of this Kelly tree. And well, it shows you some scaling behaviors which produces self-similarity and fractality, and that's you like to work with. And you would couple this
You bring
observation.
out the word levy, so let me ask, is there somewhere underneath all this some proof of something like levy stability?
Exactly.
Which is of course fundamental to the levy walk game, right? And
That's where I wish to arrive.
no, I'm sorry, is the answer yes or no?
Yes,
Yes, okay.
yes, yes. This produces a levy. It's exactly what produces a levy noise. I just wanted to take this step to say that we actually have some resonances, and we will look into a Chirikov parameter, that is nonlinear frequency shift the distance between resonances. Then apparently it goes as number of states to power 1 minus s. So when s is 1, there is no dependence on number of states. But if s is smaller than 1, then of course k is very naturally becoming much larger than 1. So you have always a stochastic and very chaotic behavior for that n larger than 1. So this observation coupled to the previous slide for Kelly trees would basically bring you to the conclusion that what we have here is a levy noise. And I would use it as a driving source for particles in a sense. So the idea out of this slide is that coupling between oscillators produce a levy noise too. That is, if you imagine your staircase jets, they can be vibrating. At least this is the physical picture that I see. Vibrations of staircase jets produce a noise process. But this noise process will not be just Gaussian noise, it will be levy noise in a strongly coupled system. And this levy noise then can act on particles, already on plasma particles. We have not particles so far, and will push them in radial direction. So what we'll have in the end, we have a particle, and these are waves produced by vibrations of the staircase jets, and pushing the particle, they would act statistically as a levy noise. And then we end up with this system of equations. That is equations of the motion of the particle for radial direction driven by a levy noise.
Sorry. The fact that this levy noise is related to the fact that S is a fraction.
Yes. Yeah. If S is 1, it's Gaussian. It's not interesting. So that's it. I obtained this sort of equation, which are sense a Langevin equation, stochastic equations given by levy noise. And this type of equation was studied in statistical physics. The hard result here is that based on this equation of motion driven by levy noise, you derive statistically an equation for phase space dynamics, for probability density to find the particle at time t, at position, with velocity. And that sort of equation will be a generalization of Klein-Kramer's equation. More specifically, it will be fractional Klein-Kramer's equation. The derivation exists. It's a bit tricky, and I have to omit it. It's not a simple thing, but there is a derivation starting from Langevin equation, arriving to Klein-Kramer's equation in phase space. But we are not willing to work in phase space. We wish to work in a real space. So then there is a next issue to reduce your Klein-Kramer's equation to an equation in a real space, which will be Einstein's Milankovsky equation. This reduction is not always possible. But if, like we used to have in a plasma, we have some viscosity, then above a certain level of viscosity, we basically can reduce Klein-Kramer's equation to Einstein's Milankovsky equation. And that will be basically a kinetic equation for transport in real space only, driven by Levy flights. And this is hard result now. Maybe 20 years ago, it was not hard result. It was not known yet. Now it is known. So starting from stochastic differential equation, we derive fractional Klein-Kramer's equation. Then in the presence of Coulomb collisions, you can reduce it and obtain a transport equation and configuration space only driven by Levy flights. And that's what gives us this model, essentially. This will be the kinetic equation and configuration space only. So the partial T term, some potential term, and a term which incorporates collisions and Levy flights. So this is derived. Somehow, you know, in my talk, I chose a little bit counterintuitive maybe approach, or I went against of time. I reversed time. First, we obtained this model, we call it COMP model. It was my work with Jens Rasmussen from 2018, yet in 2014 we had another work. But first we obtained this model and we used some continuous time random walks to derive it. Well, it was also derived in this fashion by other people, but we were probably the last who derived it in that fashion. And then we understood that this kind of equation can be obtained also from the nonlinear Schrödinger stuff. We did not know it in 2018, but now we know it. So we had this equation, and that was a COMP model. And the COMP model, why is COMP? Because we postulated that this spikes due to the staircase self-organization, it can be modeled like some sort of sawtooth potential with some spikes here, and we could also speculate about the shape of this spike here. So we could quite play about just putting here, for instance, some sort of power law behavior, then just dropping it, power law, dropping it, and we're looking how the solution to this equation would be organized. It's just an interesting, I would not say exercise, because it leads to very interesting conclusions now. Before I show it, well, the COMP model contains a very clear partial case that is a free Levy particle. So when you neglect potential force term and you neglect sources and sinks, you get an equation for a free Levy particle. So it's an equation for Levy flights. Then for Levy flights, you know what problem is. That if you solve it, then asymptotic behavior of the probability density is such that it's rather slowly decaying with the space scale. So if you calculate mean square displacement, then it diverges. And it's in many ways, it's mathematical, but not sometimes very physical. And this is a problem with Levy flights. Well, anyway, the new thing, however, coming with the COMP model is that you can find the Levy flights. So if you put them now in a potential well, that's what we did with Jens. We said, okay, we don't wish anymore to work with a free Levy particle, but we put it in a potential function. And the potential function is due to the staircase self-organization. So maybe you could speculate some form here. And if we take this form as a power law, then the hard result out of this equation is that apparently you can do something with the Levy flight. That is, you obtain a probability density which starts to decay faster at large x, so fast that mean square displacement becomes finite. It becomes finite if the exponent of the power law here goes faster than 4 minus mu, where mu is the exponent characterizing the Levy flights. That is the conclusion here. If you put a Levy particle into a potential field, then you can kill the divergence of the mean square displacement, and the divergence is eliminated, and the mean square displacement becomes finite. And this is good, because when you have something divergent, it's either a signature of a new physics effect or there is something wrong in theory. So we got it with a potential field. And then we wish to put it.
Let's say 5 minutes is okay?
Yes, yeah, just. So we then put it into a potential function and we calculate the behavior at small x and large x, and then we can calculate probability density, which goes like exponential core and power law tail. And this is immediate consequence of the potential field. And then we can calculate, of course, the size distribution of jumps in radial direction, which in this business would be a size distribution of the avalanches. And we calculate then this branch here. And this final step would be to consider that this is periodic, and we actually have not really power law going to infinity, but we have a periodic occurring spikes. So there is another branch here, and the whole thing for size distribution goes this way. And the tricky point is that the steeper decays here, the higher the jump here. So the better is the confinement between the staircase jets, the more probability that you have some events going outside the confined region with the greater size and greater probability. And this is dangerous well, Guglielmo actually could see it in a gyrokinetic simulation, and he obtained a behavior which was very just reminiscent of what we saw from the comp model. But there was one problem here. The problem is that this is a power law, and the power law function is not a Gaussian. I mean, when we say that we localize our Levy flights by putting them in potential field, we still don't obtain exponential decay of the probability density. We still have it as a power law. And this means that there is an enhanced probability of under-barrier propagation. And that means that there is an enhanced probability of big events. And that's what Guglielmo saw actually in his simulation. So he indeed observed a surge in the heat very occasionally occurring in the plasma system with staircase self-organization. And this surge is actually seen, not seen on flux surface average profiles. So when it moves, there is no signature of on this flux surface averaged profiles here, which means that this guy here occurred entirely by the self-organization of internal self-organization of the plasma. So something was just redistributed like in self-organized critical system. You don't put stuff inside, but you just redistribute your existing stuff in the lattice. And this was a big event. It was something that apparently occurred. It was a rare thing. It was not quite usual that you can see it, but you can see it. So we were very inspired by all this business some times ago, and even wrote two other inert proposals suggesting to study these events. But we can bring sometimes a camel to a river, but we cannot force the camel to drink the water. So for us, it was quite conclusive, however, that we may be dealing with big events in a system with power law decaying probability density. And there was some business also to characterize the different events. I'm sure you're familiar with the black swans, but there is other more dangerous guys probably. So we were discussing all that in a specialized conference. And Leiden ran a workshop for just dedicated to the study of extreme events in various fields, including fusion plasma. I was quite inspired essentially by this poster, which I had to insist with some other organizers willing to put some other kind of dragon. I believe dragon must be Chinese. So that's it. I had actually a few more slides left. Well, just I might be showing you how to deal with a nonlinear Schrödinger equation with a quadratic nonlinearity, and how, based on this equation, one can obtain some sort of thermodynamic equation of state, which is polytropic equation, and using the number of degrees of freedom in polytropic exponent, just predict self-consistently the distribution of avalanches, and to compare it with the results of Guglielmo's simulation using Gisela. Just I conclude to saying that the final convergence was very fine. That is, we got numbers, which in this theory goes with this strange mathematical argument. We got some strange numbers, like organized with square root of 17 with something close. But it produces us the slopes in the numerical simulation that are very close, in fact, to what is seen in the simulation. And this gives us actually the inspiration for future work. So thank you for your attention.
Time for a few questions. One actually, it was not clear to me how you chose the potential. Is it coming from simulations as well, or?
No, well, if we are serious, we of course have to say that it has to do something with the vorticity and how the spacing between the staircase jets is organized. Then we have to really go into plasma physics stuff. But in this model, we just say that, well, jets work as semi-permeable transport barriers, and we just speculate a suitable toy form for this barrier, which in our model is a power law. And then we see the effect of the power law on the confinement properties of the Levy flight.
Yeah. Maybe trying a different wording. Of course, Pat's question is a central one. So can we derive that from plasma-related topics? That's an open question. But a lot of people in this room basically use a lot of equations because at some point they show some interesting behavior. And here I think the key point is that, as Alexander was showing, we started from the result. The result is that you have a quasi-periodic set of zonal flows connected to avalanches. The avalanches are going to be described by a Levy process. I'm going to connect the zonal flows, and all of that is put into a kind of an oscillatory point of view. So you have a network of oscillators, and you know that you have a very rigorous derivation from the nonlinear linear all the way to what Alexander showed. And the real prediction is that this rigorous pathway gives you a prediction of the distribution of avalanche sizes, which is a prediction. And then you can compare it to the numerical results. And the interesting thing is that the shape of the distribution function of those avalanches, what we interpret as the connection between those oscillators, actually fits quite well with the simulation results with no fitting parameter. That's the first of what Alexander has been able to show.
Maybe I understood completely nothing, but is this in some way that tell us that inside the staircase region we cannot use the Fick law but fractional derivative approach? And if so, how can we choose the right order, the right S?
Great. You understood everything. You ask a question. Exactly. We have avalanches, which is a non-local transport, and just an avalanche propagating ballistically along radial direction, which would be a Cauchy flight. Then I did not show it to you because I thought it was a detail. But of course, when I derive this number S with square root of 17, I would say that there is some argument there that refers to the fact that the staircase occurs at some sort of marginal condition that is similar to self-organized critical state. And this marginality is that the Cauchy flights are at the edge of being localized to localized. Okay, so you have a condition that the Cauchy flight must have the behavior such that it is at the edge of the localization. It gives you the condition on the alpha parameter, which is the parameter which shapes me the staircase physics. So that is at the margins. Then the rest you weakly localize, weakly with the power law. And then, yes, if you just write an equation for Cauchy flights, you have exactly an equation for Levy flights and the limit of the Cauchy limit with potential function. That's how it works.
Okay, so other question is again.